Thanks for inviting me. Today we are going to talk about the logic locking. That is a topic that have been evolved over a decade, and it has been used for different purpose. I mean, the basic purpose was to lock the IC. I mean, to lock the functionality of the IC. So let's move towards the a little bit introduction. So as we know that in the past there were no machines, no ICs, no electronics. So people were also using the kind of cryptography, cryptography or encryption or locking mechanism. So they were trying to send envelopes. They have to convey the messages, and they were using different techniques in 200 years ago, right? And they were using different mechanisms. For example, in this table, one of the researcher he analyzed the letters from the 1800th century, and he actually discovered that there were multiple techniques, and they were based on fold, duck and slit techniques, and they were trying to hide the ladder in such a way that whenever someone will open, and they will not they will actually tear the ladder, right, the paper, and the message will be destroyed. So that kind of the fact is also, it was existence in the we can say literature. And then this was kind of a motivation for many researchers, so that we can continue. And and also we can say the cryptography, it is not 200 years old story. It has been in centuries. Like, for example, 1000 years ago, there was also a way to hide the things and send to the other countries. So keeping this motivation, let's move towards the IC design space. Like, so we know that these days many of the companies, they are actually utilizing globalized IC supply chain. What does it mean? That this means that something is happening here. For example, IP is designed in California, and after that they design chip in, for example, Arizona, and then they send this chip to Taiwan. Then they manufacture, fabricate, then it will be sent to, for example, China. So they have to assemble, and then send to the Korea, for example, for testing and so on. So in this case, for the whole the IC design supply is globalized, right? And the fact is that this is the reason that many of the companies are fabless, which means that they do not have on-site facility to fabricate the IC, right? So the reason is that building and maintaining the foundry, like TSMC, or it requires $1 billion, which means that it has skyrocketing cost of building and maintaining, and also it requires the other the requirement. So if we analyze this graph, right, if we can see here that with the passage of time, there were only few foundries that were left to fabricate the ICs on advanced technology now, right? For example, today we have 3 nanometer technology now, right? And there are only few of the foundries that can fabricate, for example, TSMC, we can say, or maybe Samsung for sure, and maybe Global Foundries or Intel, right? So that is the fact that the whole IC design space is actually globalized, and this is fabless companies, and they outsource, after that, as we know that we have actually globalized IC supply chain, but we have very different problems. Instead of designing, maintaining which part should go there are other problems that are related to the security. And we have the flow is here in this figure. We can see we have system specification, right? This is a globalized IC supply chain and the design flow, right? Then we have multiple third-party IPs that we have to use. We have design and integration stage, right? We do the logic synthesis and convert into the the gate level netlist, right? After that, we perform physical synthesis, we place and route and do the sign off, and then send the layout to the foundry. And then we have fabrication. We have the testing and packaging deployment, right? That, as I mentioned earlier. So we can see that this whole globalized IC supply chain and design phases are, highlighted in, and the red and green color, and we can see that these red color are untrusted stages, and there are multiple security threats that emerge from these untrusted stages. For example, reverse engineering, overproduction, hardware trojan, IP piracy, counterfeiting, forward injection attacks, and side channel attacks. Right. So there is a lot, and we need to cover this security. Right. So let's discuss these threats step by step. What are these actually? Right. So reverse engineering. So reverse engineering is like that. It can be happen on user phase, or it can be happen in the founder phase, right? So reverse engineering is that we try to get back the logic, and there are two types of reverse engineering. One is the physical reverse engineering, one is the logic reverse engineering, right? For the physical reverse engineering, we have to decapsulate, depackage. We need to see the die here. Here are the pins, right? And then we actually remove the package and the die case, right? And then we de-layer the IC. We have multiple layers of, and then we scan and we stitch together, and then we try to figure out what are the metal size, metal stack, VS, and then we have the standard cells, and we read out the design and we get the networks. So this is the physical reverse engineering, right? For the logical reverse engineering, we assume that we already have unknown, the net list, for example. We don't know what it is, and we try to guess that design functionality, right? And some part is missing, and so on. So then overproduction, right? Overproduction is that, for example, I am the manufacturer, and I try to go TSMC and say, hey, produce 1 billion IC, right? And then they produce 1.1 billion IC, right? And then the remaining one, we have no control. We cannot go there and check that how many ICs you are produced, right? And then they overproduce and sell into the gray and black market. So this is the fact with the overproduction, and this is also a threat. And then there is an interesting hardware trojan threat, right? This is very interesting, right? So this is kind of a thing. You try to embed a very small piece of logic, which is a malicious modification into the IC, and you are a user, your time to market is already tight, and you cannot control, right? So I mean, they can actually degrade the reliability and robustness. For example, they put trojan just to leak the power, right, or disturb a little bit of the timing. And and on the other end, for cryptographic, they try to leak the information so that we can steal the key from the cryptographic core, right? So that is the hardware trojan, and it is quite famous, and it exists literally in the industry, and there were a number of reportings of the cases. And then we have the IP piracy. IP piracy is also the biggest problem in the hardware security domain, as in the globalized IC supply chains. And we can see that when we send the IC to the foundry, they can easily, they know all the transistor details, they know the layer details, they can easily understand this is a block, this is a core, this block can be actually removed from, and then they can see that this could be a third-party IP, and these IPs could be stolen, and they can do whatever they want. So why is happening? We cannot say that big companies actually they try to do. Maybe there is a rogue element. There's an employee in the foundry or someone else, right? And then if you can see that the United States experienced a lot of loss in billions. It was reported in 2022, and then still it will be more than this number, right? And then we have counterfeit IC. This is the biggest problem with the analog IC, right? With digital also, but usually with the analog. So what is that? When we try to assemble, we ask someone that, okay, can you please assemble my stuff? They might replace your IC with the counterfeit, with the same IC, same functionality, but it was used, in the computer or in any other PCB, and they try to replace it, and then actually that IC is, has low reliability, and it is a degraded, right? It's not a genuine one, right? So that is also the problem. Then we have fault injection. That actually try to disrupt the operation of the hardware, right? They try to inject multi-bit, single-bit fault. There are many techniques for fault injection, in general, right, they try to disrupt the functionality, and sometimes they want to bypass the security mechanism. Just to give you a hint, for example, they try to bypass the secure port, and we can do with the fault injection also. And as I mentioned earlier, a side channel, right? Side channel, they actually leak information in the form of power, timing. It could be like acoustic signal, it could be electromagnetic emission, right? So there are many forms of the leakage for the side channel, but one of the famous attack I actually also performed many years ago with my hand. It was a power-based side channel attack, right, to steal the key from the cryptographic code such as AES. So these are the attacks. They exist in the nature. What we can do, how we have to prevent. So in 2008, this was a technique, we call it logic locking. And this technique is called hardware obfuscation. What is obfuscation? Obfuscation means that we try to hide a logic behind the secret, right? Or logic locking, we lock a logic behind a secret. So it means that if we see in this example here, we have here a very simple circuit with 3 inputs. What we do, we try to, the first approach is that we try to insert random XOR and XNOR gates, which means that we have embedded some key bits, right? And these key bits are stored in the tamper-proof memory, right? Tamper-proof, we cannot tamper that memory, and we have the keys there. And then we have correct key here, right? And then we have a correct functionality and the correct output. Unless else we have a wrong functionality. This was actually invented in 2008. And then what happened with this technique? There were many other versions of this technique, and they were actually, in the research community. So this technique was used, and it was effective at that time. And then we discussed this one, right? This technique is called random logic locking. It was the first one with the flavor of logic locking. After the random logic locking, we have a technique, we call it fault logic locking, right? We try to inject a fault in a circuit. For example, here we can see the same circuit, right? If we put stuck at fault here, right, and this fault will be propagated, and then we have a corrupted output. So if we have this gate here, we embed the gate. So the fact is that previously we were, just placing the random gates, and then we have a keys. Here we are identifying the reasonable fault locations where we have to put the faults, and then we try to embed the key gates. This is called key gate, which has key. And then, so if we embed here the key gate, this key gate is actually, injecting the fault in the circuit. Now we will have to cancel this fault, and we have another key gate that we have embedded here, and we have this key, and this will actually cancel this staggered fault, and then we get the correct output. So this is called fault, logic locking. So what happened that there was a lot of attacks that were also proposed, and the first one attack that was proposed for logic locking, it is sensitization attack. So if I give you a basic idea, how does it work? Let's take this locked circuit here, right? And then if we have a key here, key 1, key 2, and if I try to set the key X and try to, get the input pattern, right? So if I have input pattern, and then I will take the working circuit, I will go to the market, and I can get a chip that is actually a working circuit. I know the inputs, and I can get the outputs correct out from the working circuit, which already has a key, right? So if I give the don't care here and the identified pattern, right? And then this key bit will be actually sensitized immediately to the output, and then I can get a half of the key. And similar is the case with the K2, it will be sensitized here, and because this is the inverted gate, XOR, right? Then we have inverted output. So I will check with both the inverted output and the normal outputs, and then I will try to try to we can say add both of the parts of the key, and then I will get the key. So this is the case that it was also a problem that we need solution to. After that, we have another technique that was kind of, we can say, um, it was strong logic locking. And in before I starting to define some other terminologies, so we have two different type of the attack models. So there were that are classified into oracle-less attacks and oracle-guided attacks. So what is oracle? Oracle means that, as I said earlier, if I go to market and I get a product and I deassemble the IC, and then I have an IC, I know the input, I know the output. If I give the input pattern, I will get the output pattern, right? So this functional IC is actually called oracle in the hardware security domain or logic locking domain. So I have two types of the attack. I'm using the functional IC that I can get from the market, oracle-less attack, or oracle guided attack, or without oracle-less attack that I don't know, the oracle is kind of black box attack. So after the strong logic locking, if I tell you, there was a very successful attack in 2015, and this attack actually is SAT guided attack, and it is very famous. We call SAT attack, right? So in the SAT attack, it actually broke every 3 or 4 types of the logic locking techniques in seconds. It just ran and it tried to break the key in second. So to give the idea, we need how this SAT attack works. This is a basic flavor of the SAT attack. There are many other types of the SAT attacks, and I will discuss later in the later slide to give the idea. So if we see in the oracle guided attack, right, we can see that we have a basic SAT attack, and then as I said, we have AppSAT, we have double dip, fall. So these are our the attacks that are for the logic locking, and they are actually given I will mention the reference also soon. On the oracle-less attack, we can see we have structural analysis. So structural analysis is the thing that we try to see some traces in the netlist. We have the gate connections, we know it, and we try to build the cones from input towards the output and try to separate, divide and conquer the circuit and try to get some of the information from the netlist and from the netlist idea, right? And then we have simulation-based logic attack, and then we have the delay. These are some advanced concepts for the sequential logic locking, so we will not discuss here. Okay, so with the SAT attack, we need a circuit that is called MITRE. MITRE is kind of a very simple circuit. We can say it's kind of until here. If you exclude this one, this gate, this is the simple comparator, right? So we have two different copies of the locked circuit, right? Locked circuit that we, without the key, right? And then we have one locked circuit, other locked circuit, and if we give any key bits, we don't know the correct key, and then we get some output, right? And then we try to compare and we try to see the mismatch, right? And when this diff signal is that, right, then it means that these two keys, right, they are not equal, and we get a differential input pattern. We need to get a differential input patterns for the SAT attack. So if we come to the SAT attack here, we can see we have the locked netlist L here, and we have functional IC that is oracle, and then we need to find a correct output. So this is a MITRE that I illustrated here, and when we have differential signal, we get ID, which is called differential input pattern. We take this differential input pattern and we give to the oracle, and we find one output, right? So after that, we have two other copies of the circuit, and we try to take this output and we try to embed in the CNF formula, right? And then we have two different type of the keys because we need the zeros and the inverted for example, we have 001 and then we have 1110. So we need two sets of the copies, and then at the end it will return the key here. It will do the SAT formulation here. So a little bit advanced concept, but to give you idea, to give you a curiosity, what is the SAT? You go to the internet and search SAT, and I have a lab for this one, and I'm happy to provide for you guys also. And I mean, if someone want to explore more, how does this SAT works? So let's move forward. After the SAT came, there was a lot of discussion that okay, this logic locking is broke, and then we should come with a new idea. And what happened in the last decade? There is a burst of the technique. For example, these three techniques, they were pre-SAT, and after the pre-SAT, we have bunch of techniques: SAR lock, SFFL, CAC, blah blah blah, and there were a lot of attacks. SAT, then there was a hill climbing is kind of heuristic attack, and then we have scope. This is called resynthesical attack. Removal attack, it is that we try to remove some part of the circuit and give the key, and then we try to I utilize divided concurred approach. So a lot was happening with this. This one is the reconfigurable based obfuscation that we will discuss later, right? So when until 2018-19, the community was really anxious that they want to actually get rid of this logic locking. One guy just proposed the one technique, he just add something else, and then there's another attack. I mean, what is the what is this cat and mouse game, right? And started, and then and the fact is that the defense agency here in the United States, they funded this project a lot. They funded this project for more than a decade, and then they realized that this is not a useful approach, right? But it was used in different instruments and so on. Okay, so there was an active call. Okay, we need to say that logic locking is that this technique is not working. We need to find another way. So during that area, there was few people that came with an idea of reconfigurable based obfuscation, and I was one of them at that time in 2020, right? At that time, what happened what is that technique, right? So the technique is that here in this layout, we can say that we have embedded FPGA. It is FPGA which is embedded into the ASIC, right? So we call it embedded FPGA, and we can also get this embedded FPGA from different third-party foundries, right? You can embed. Okay, so what we have to do that we need to take the logic, we need to find a critical or sensitive part of the logic, and then we keep that logic as minimum as possible and try to map this logic to the eFPGA and generate a bit stream. The rest of the logic, the majority of the circuit, it will be mapped to the standard cells, right, as usual, as we have right in the layout. Then we embed this eFPGA and we send this to foundry, and then it comes back. For the foundry, we don't have a bit stream here, and this logic is hidden. So the partially the circuit is locked. Once this chip will come, we try to feed the bit stream. We recover the functionality, and then we have the correct functionality of the IC. Okay, let's compare this with the logic locking. What happened? If we move from left to the right, what will happen? In case of the logic locking, we have a less PPA, power, performance, and area. We have less security, but here we have more security, high degree of security, and we have more power, performance, and area overheads, right? And this guy, the eFPGA, it is coarse grain. Coarse grain means that it is placed there, it is stick there, the logic is combined, it's not spread over the layout, and someone can easily recognize it, from the reverse engineering or from the, if we do the SEM images, for example, right, of the layout. For the logic locking, we have the key gates, right? These are the key gates. They are actually embedded into the logic, and they are spread all. And this is fine grain, right? Fine grain means that they are spread. If we have rice, in the plate, they are spread everywhere, right? Okay, so this has much different granularity. Granularity, as I defined, the coarse grain and fine grain terminology, and then we have also problem with the LPP and the the we can say security. So this technique has been proposed, and then we have like a bunch of the other techniques. And then the one I proposed, it was a different idea, because here we identified that we have the problem with the power, performance, and area, and it is a big problem in the industry. No one can bear a high silicon area and lose the performance. So I come with an idea with the hybrid ASIC. So what is the hybrid ASIC? We have here the the FPGA reduction, as we discussed earlier. We have traditional ASIC. In the center of these two guys, we have a hybrid ASIC. Hybrid ASIC utilize reconfigurable elements. As you studied during the course, FPGA has LUTs, right? So these guys are the LUTs. We call it macro in ASIC, right? If someone knows it. So these macros placed, and they are fine-grained, and they are distributed all over the layout, right? So the fact is that if we see from here to here, we have more flexibility, right? And more obfuscation. And if we move from right to left, we have best-in-class performance here, and but that is the static ASIC, right? We cannot change the logic anymore. So in that case, this provides us flexibility, right? And this hybrid ASIC, so that we can also reduce the intensity of the security, and we try to come with a midpoint solution where the designer says that, okay, I can bear this power, I can bear this area, and I can have this level of the security, right? So this was the technique. It is still not broken, and there are few attacks, but they just get very few partial keys, right? And it's still not broken. And the reference is given here, and someone wants to study. He or she can read the reference. Okay, so to give you how does it look like in silicon, we have this one layout of AES, right? And this is, and in this case, 80% of the design is obfuscated. It means that 80% of the design is reconfigurable, and it has LUTs. So if we see the magnified view here, we can see how good or how fine placement is the LUT of the LUTs, right? And then we can see that we actually exploited the spaces, the empty spaces between these LUTs, and then we placed the static logic, the logic that was not obfuscated. These are with the red color, and these are the standard cells. And this was actually, done with the 6500 TSMC foundry. So, so here I could actually conclude my presentation, and we see that what happens that we actually saw that logic locking has been evolved. It was a good solution. It was, it got a pressure after the SAT attack, but it doesn't make any sense. And people are working in this technique. You will see a lot of papers. But no, you will not see any sensible, well-known research in hardware security working on logic locking anymore. And then, SAT attack actually changed the game. It actually, showed the vulnerability in this, we can say, logic locking. And then we actually catered this vulnerability with, reconfigure-based obfuscation, revo. For example, FPGA reduction and HASIC, and which emerge as a new hardware security obfuscation techniques, right? And the beauty of this HASIC is that it gives us a flexibility to choose the designer what I want actually, and choose the designer between design versus security trade-off, right? To make it a design versus security trade-off. So that is the fact. Thanks for listening to me, and I'm happy to answer any question and any detailed discussion you want.
And audience that want to ask a question, Ms. Zoha Kamat, you can turn on your mic and ask a question.
Okay, thank you, sir. Am I audible, Mr. Zain?
Yeah, I can hear you.
Okay, sir, you presented a really good work. I just wanted to ask initially, you just presented the idea of a hardware Trojan, the backdoor is a same thing as hardware Trojan. as we all consider, most of us all consider Mark Tahani from University of Florida, his work as Bible in this hardware security field. He actually proposed one of the idea of hardware Trojan scanner, right,
Mm-hmm.
in one of his papers. So with this, I'm most of the researchers and the scholars for the detection of a hardware trojans in OEM ICs, what they do is actually for in a sense, they just they just they just synthesize the code, or added the code on FPGA and stimulate it, and then by identifying its power and emissions, they're saying, okay, we are actually detecting the trojans by finding the power, extra power, and the emissions. I just wanted to ask, is there any and also in this Mark Karani paper, that when he's proposing hardware Trojan scanner, what he actually tells us that, okay, take the SAM image of a OEM IC, and then for the testing IC, take the SAM image of that IC and then match them, if there is any difference of a logic of a gates, and then you can find that. In most of the cases, destructive approach, invasive approach is not feasible because of the equipment, because of the expensive, because of the cost involved in the process. How would you say? How would you suggest, sir, the detection of a hardware Trojan, as per as per my little knowledge? I think if the OEM is actually inserting any kind of addition and subtraction in the design, we being at the end user, we being at the cyber security expert or the hardware security expert, we are actually unable, we are not at that position to identify the Trojan itself if it is embedded by OEM. Is that so?
So the
Or
fact
is
is
there
that
any work? Is there any work other than this FPGA design side?
so the fact is that I know him very well. He's working for a lot of it's for a lot of different things. And the fact is that if you take I mean, at CMU, we never worked with them Florida guys, I can tell you. So this is a different way. But okay, we cannot say that we synthesize the design. I will map to the FPGA, and then from that power, I can easily try to track that, if there is a Trojan or not. Because the fact is that we have ASIC IC on different technology, and we have FPGA that is actually on a different technology. One of the point. The other point is that even we have a same technology node for FPGA and the IC that we are going to detect the Trojan, then we even have a timing delays, right? So so it's very hard to detect from the FPGA. FPGA has different architecture. It will burn different power. You cannot get a static power, because static power is different from your IC, right? So that is the point. For the other point that you said, that how to match the the layouts, and then we try to identify the hardware Trojan. I can tell you that there is a camouflaging, right? We have a camouflaging cells. We can really do. I mean, Dr. Rashid can easily do in custom camouflage cell that actually looks visually the same, right? But they are different in logic. But then you cannot interpret that, okay, it is a hardware Trojan or not from the visual inspection also. So that's why it depends on the different, different type of Trojan needs different type of the techniques. But if the adversary is really clever, it's really hard to detect the Trojan. That is the end result. The techniques are there for sure, right, for the different non-Trojans. Yeah, thanks. So thanks for inviting me. If you have any question, any of them, I'm happy to answer in email. Thanks.
Big round of applause for all of the audience. Thank you very much, sir. We are signing off from today's session. Allah Hafiz.
Allah Hafiz. Thank you. Assalamu alaikum.